This is the first class of magnetic effect of electric current. The first topic is Oersted experiment. First topic is Oersted experiment. The basic part of Oersted experiment is already done in class 10. And the conclusion of the experiment is that when a current flows through a conductor, a magnetic field is produced around it. We know that Earth behaves like a magnet, and therefore, if a magnetic needle is freely suspended on the Earth's surface, it always aligns along the geographic north-south direction. If a magnet is freely suspended, it always aligns in the north-south direction. Always align. It is because of the Earth magnetic field. Okay? So this is the geographic north, geographic south, geographic east and geographic west. Now in the Oersted experiment, what we have to do, we have to stretch a wire AB between two stands. And the wire has to be placed in the geographic north-south direction. That means I stretch a wire AB. I stretch a conductor AB between these two stands in the north-south direction. And with the help of battery, a battery is connected using a key between the two end A and B of the wire AB. Now, I place 4 magnetic needles. This is the needle 1. This is the needle 1 below the wire. This is the needle 2 above the wire. This is the needle 3 along the axis of the current carrying wire. And this is the needle 4 along the, that means this needle and this needle, these two needles. You just see, these two needles are very close to these two ends and they are parallel to the length of the wire. Okay, this needle is below the wire and this needle is above the wire. Now, as soon as we close the key, what we will see, when we close the key, a current flows through the wire in the direction from B to A. And then it is found that these two needles get deflected. But no deflection is observed in this needle and this needle. And what is the nature of deflection of the needle which is placed below the wire and above the wire? And the nature of deflection is exactly opposite. You just see the needle placed below the wire get deflected towards the west and the needle placed above the wire get deflected towards the east. When current flows through the wire, the needle which is initially placed below the wire get deflected from north-south direction towards the west, north pole of the needle. The north pole of the needle get deflected towards the west and north pole of the needle which is placed above the wire get deflected towards the east. Now if we change the direction of current, that means if I change the polarity of this battery, again I observe the deflection of this needle and this needle. But no deflection is observed on this needle and this needle. This means that a magnetic field is produced. A magnetic field is produced above and below the current carrying wire, but no magnetic field is produced along the axis of the current carrying wire. When we change the polarity of the battery, then direction of current changes and the needle which is placed above and below the current carrying wire get deflected again, but it is now in opposite direction. That means north pole get deflected towards the east when it is placed below the wire, and the north pole get deflected towards the west when it is placed above the wire. Okay? But for that, we have to change the polarity of the battery. That means current has to send the current has to send from A to B. So from this experiment, we can make following conclusion. When current flows through a wire, magnetic field is produced around the current carrying wire. Magnetic field is produced around the current carrying wire, but not along the axis of the current carrying wire. Is it okay? Number 2, the nature of magnetic field on both sides of the wire are opposite to each other. The nature of magnetic field on the both sides of the current carrying wire are opposite to each other. Why they are opposite to each other? Because here the needle get deflected in opposite direction. When current flows from B to A, the needle which is placed below the wire, its north pole get deflected towards the west, and the needle which is placed above the wire, its north pole is deflected towards the east. So therefore, the nature of magnetic field on both sides of the current carrying wires are opposite to each other. So these directions can be remembered with the help of the right hand thumb rule. You just see, so this is my right hand, and this is my left hand, and this is my right hand. Okay? You hold the wire, say this is the wire. With the help of my right hand, I hold the wire. Then if the thumb, you just see, this is the thumb, no? If the thumb directs the direction of current, then curl of the finger, this is the curl of the finger, represents the direction of magnetic field. So if my needle, say this is the wire, and this is the directions, then what happens? So this is if the thumb represents direction of current, then curl of the finger. How the finger curls? You just see, the finger curls like this. The finger curls like this. Have you seen it? The finger curls like this. So this is the wire, the finger curls like this. That means the direction of lines of force will be like this. You just see the rotation. Therefore, the needle which is placed below the wire get deflected in this direction, and the needle which is placed above the wire get deflected in this direction. So this is the nature of the deflection. This is the nature of the lines of force around the conductor. So this is the rule. If we grasp the conductor with the help of the right hand, if the thumb directs the direction of current, then curl of the finger gives you the direction of magnetic field around it. And what is the third conclusion? For a straight wire, the magnetic lines of force, we know that the magnetic field and electric field, they are represented graphically with the help of lines of force or the field lines. So for a straight current carrying wire, okay, magnetic lines of force around it are concentric circles. And number 3, when current flows through a straight wire, along its two ends, no magnetic field is produced. Say this is the current carrying wire. Along this direction and along this direction, there is no magnetic field is produced. Along these 2 points, no magnetic field is produced. Is it okay? This is all about the Oersted experiment. That means Oersted experiment gives us, the Oersted experiment says that, concluded that a magnetic field is produced around a current carrying wire. Our next topic is the Biot Savert law. From the Oersted experiment, we know that when current flows through a wire, a magnetic field is produced around it. Now, with the help of Biot Savert law, we can find out what is the value of magnetic field intensity. One point is very important. For electric field, we say electric field intensity. But for magnetic field, it is proper to say magnetic field induction. It is proper to say magnetic field induction. For electric field, we define electric field intensity. But for magnetic field, we define magnetic field induction. So this Biot Savert law gives us the value of magnetic field induction due to a current carrying wire. When the wire is very long, we generally cut the wire into small pieces. And this type of small section of current carrying wire or small section of current carrying conductors are called the current element. So this is the wire. I cut the wire into small sections. Okay, each of length dl. So this small section through which current flows is called the current element. Okay, so what is? This is the conductor through which the current flows. And due to this current carrying conductor, I have to find out a magnetic field at a point. We have to find out the value of magnetic field induction at a point or strength of magnetic field at a point. And for that, I have to use the Biot Savert law. What is the procedure? Instead of considering the entire wire, we consider a very small section of the wire. That means we cut the wire into small pieces, each of length dl. This small piece through which the current flows is called the current element. It is said that magnetic field is produced by this current element. We know that electric field is produced by electric surges, but magnetic field are produced by current element. We may say, yes, magnetic field can also be produced from magnetic poles. Magnetic pole, magnetic north pole, magnetic south pole. But it is not possible to get an isolated magnetic north pole or isolated magnetic south pole. It is not possible to get isolated magnetic north pole and isolated magnetic south pole under laboratory condition, and therefore it is better to say the source of magnetic field as a current element, not the magnetic pole, because magnetic monopole does not exist. So this is the current element. This is the center of the current element. I have to find out magnetic field induction at the point P. You just see, so this is the wire. I have to grasp the wire like this. When I grasp the wire, because the current flows like this, my thumb will be in this direction. When I grasp the conductor like this, in which direction this forefinger of my right hand goes? It goes inward. Yes or no? Therefore, magnetic field at this point will be perpendicularly inward. Therefore, this cross symbol is given here. So, if the magnetic field at this point is the perpendicularly inward, then magnetic direction of magnetic field at this point becomes the perpendicularly outward, because for a straight wire, magnetic field lines are circular. It will be like this. So, if we want to find out magnetic field induction, it will be outward. You just see my finger. It will be outward. And here it will be inward. Okay? So this is the cross. Why it is written dB? We consider a small section of the conductor. We consider a small section of the conductor, therefore magnetic field produced is also small, dB. Okay? So what is this law say? What is this law say? This law states that the magnetic field induction due to a current element IDL at a distance r, at a point P, which is at a distance r from the current element, is given by dB proportional to IDL sin theta by r square. This is not a theoretical law, it is an experimental law. Due to this current element, magnetic field induction at the point P, which is at a distance r from the current element, is given by dB proportional to IDL sin theta by r square. What is I? I is the strength of the current. What is dl? Length of the current element. What is theta? Theta is this angle. Sometimes in some books, this angle is also considered as theta. But both of them are correct because sin theta is equal to sine of pi minus theta. So if I consider this angle theta, this angle is pi minus theta. In second quadrant, sine is positive. Okay, what is theta? Theta is, this is the theta. Theta is the angle made by position vector. What is called position vector? This r is called position vector. This position vector represents the position of the point P with respect to center of the current element. And this is the direction of current. So theta is the angle made by position vector with respect to the direction of current. Okay? So IDL sin theta by r square. That means when the distance increases, it is in the denominator, therefore strength of magnetic field gradually decreases. Okay, so if my theta is 0, theta 0 means ki, sine 0, 0, therefore what is magnetic field around this, at this point? Magnetic field at this point will be 0. What is magnetic field at this point? Because this is the current carrying wire. What is magnetic field at this point? It is 0. Because if I consider the point P here, so this angle will be ki, pi. What is the value of sine pi? 0. If I consider this point here, what is the value of theta? Theta is 0. Because this line comes like this, yes or no? That means when current flows through this wire, here and here, no magnetic field is there. What is the value of theta? When theta is 90, dl will be here. So when the value of theta is 90, sine 90 is 1, so magnetic field will be maximum. That means Biot Savert law gives us the value of magnetic field induction at a point P, which is at a distance r from the center of the current element. And what the law say? The law say that the dB proportional to IDL sin theta by r square. In exam, only 1 mark is given to state the Biot Savert law. The question is, state the Biot Savert law. 1 mark is given. So you draw this diagram, okay? You write this part and up to this. The Biot Savert law gives us value of magnetic field induction at a point P, which is at a distance r from the current element. And the law states that dB proportional to IDL sin theta by r square. So there should be a proportionality constant, and this proportionality constant is written as mu 0 by 4 pi IDL sin theta by r square. This mu 0 is called permeability of free space. In electrostatics, when you write the Coulomb's law, can you remember this proportionality constant is 1 by 4 pi epsilon 0. What is epsilon 0? That is actually permittivity of free space. What is the value of mu 0? 4 pi into 10 to the power minus 7 Weber divided by ampere meter. Weber is a SI unit of magnetic flux. Can you remember electric flux? Electric field intensity into area, or electric lines of force that passes normally through an area, that is the electric flux. That is similarly a magnetic flux is also there. Magnetic lines of force that passes normally through an area. That is magnetic flux. What is the SI unit of magnetic flux? It is Weber. Or we may write like this also, 4 pi into 10 to the power minus 7 Tesla meter per ampere. T for Tesla. Tesla is the SI unit of magnetic field induction. M for meter, A for ampere. Okay? So if I write in the vector form, since it is sine theta, have you seen it? It is sine theta, no? It is sine theta, ideal sine theta by r square. Since sine theta, we may express the Biot Savert law in this form. dB vector is equal to mu 0 by 4 pi ideal cross r cap by r square. R cap by, what is r cap? R cap is a unit vector along the direction of r. So this is the r cap. This is the direction of r cap. This is the direction of r cap. So what is the magnitude of r cap? Magnitude of r cap is 1. So if I cut it, it is if I remove the cross product, we will get ideal sine theta by r square. So instead of r cap, if I write r vector, it is r cube. Then what happens? Ideal r sine theta divided by r cube, 1 r get cancelled. Here we get ideal 1 sine theta by r square. Okay? This vector form of the Biot Savert law is called the Laplace's law. This is already given. C is equal to 1 by square root of mu 0 epsilon 0, velocity of light. What is the value of mu 0? 4 pi into 10 to the power minus 7. What is the value of epsilon 0? 1 by 4 pi into 9 into 10 to the power minus 9. Or epsilon 0 value is 8.854 into 10 to the power minus 12. That can be written like this also. Epsilon 0 is 1 by 4 pi into 9 into 10 to the power minus 9. So here we will get this. This is already discussed. This is already discussed. That means this is already discussed when theta is equal to 0. When theta is equal to 0 or theta is equal to 180 degrees, sin theta is 0, therefore dB is 0. That means when current flows through a wire, at this point and at this point, there is no magnetic field. When theta is 90, sin 90 is 1, so dB is maximum. So due to this current carrying wire, magnetic field around this point and magnetic field around this point will be maximum. Okay? So again I return back to this form, vector form of the Biot Savert law. dB is equal to mu 0 by 4 pi ideal r cap by r square. What is the magnitude of r cap? It is 1. So it is ideal 1 sin theta by r square. Instead of r cap, we may write r vector, or in that case it becomes the r cube. Okay? Is it clear? Today I stop the class here.